Hello everyone, welcome to a new lecture in the series of Control of Mechanical Systems. In this lecture, we will be discussing of mathematical modeling of inverter pendulum. Here is the overview of the lecture. We will be starting with a brief introduction to the inverter pendulum and a description of the variables associated with it. Then we move on to the mathematical modeling of inverter pendulum. In general, an inverter pendulum is a pendulum which has its center of mass above its pivot point. And this will make an inverter pendulum as an unstable system which has an unstable dynamics with respect to its equilibrium point, which is considered as the vertically upward position or the zero angle position. Now, if we need to maintain the inverter pendulum in the vertically upward position, we need to stabilize it using some control scheme. Inverter pendulums are often implemented with the pivot point mounted on a cart. Therefore, these systems are also known as pendulum cart system or cart pole system. The inverter pendulums are used in various applications such as electric unicycle, self-balancing scooters, etc. And these are also used as benchmark systems for various nonlinear control methods. Figure 1 shows a schematic representation of the inverter pendulum, in which this is the pendulum where small letter m stands for the mass of the pendulum, and this represents the cart where capital M stands for the mass of the cart. Here, this theta is measured with respect to the vertical axis, and theta equals 0 considered as the equilibrium point of the inverter pendulum. And here we can see that if the pendulum moves from equilibrium position or the angle changes from 0 due to some disturbance, it will move away from 0 due to the gravitational force, which will acting along the downward direction. Therefore, in the case of pendulum cart system, we will try to stabilize the pendulum at its equilibrium by moving the cart in right and left direction. Here, this pendulum is fixed in the cart in such a way that it can rotate in only one axis. Here, we consider this as the origin of the reference axis, and small letter x denotes the position of the cart along the x direction, which is the distance from the origin to the pivot point. And here xp and yp denotes the coordinates of the pendulum, which are actually the coordinates of the center of gravity of the pendulum. And from here we can see that xp will be equal to x plus L sin theta and yp will be equal to L cos theta, where L is the length of the pendulum. Here we have summarized the terminologies associated with the inverter pendulum, where capital M stands for the mass of the cart, small m stands for the mass of the pendulum, g is the acceleration due to gravity, F stands for force applied to the cart, x is the cart position, xp and yp are the coordinates of the center of gravity of the pendulum, L is the length of the pendulum, theta is the angle of the pendulum. And here we will be using these two assumptions where the pendulum rod is considered to be massless and the friction is considered to be negligible. Next, we can move on to the mathematical modeling of inverter pendulum. Here, the mathematical model is in the form of some differential equation, which is obtained from applying force balance and torque balance relations. As per the Newton law, we have the total applied force will be equal to the sum of the inertia forces, where we have the applied force F will be equal to inertia force due to the mass of the car, which will be equal to m into d square x by dt square, and also the inertia force due to the mass of the pendulum along the x direction, which is denoted by Fpx here. Similarly, by applying torque balance in the pendulum, we obtain equation number 2, where we have the equation of the torque as the force into the perpendicular distance between the force and the pivot position. Here, this is the torque due to the gravitational force, which is acting in the downward direction. And here we can see that the perpendicular distance from the force to the pivot position will be equal to L sin theta. Therefore, this torque will be equal to mg L sin theta. Similarly, Fpx is the inertia force along the x direction, which will be acting in this direction. And we have the perpendicular distance from this force and the pivot position will be equal to L cos theta. Therefore, this torque will be Fpx L cos theta. Similarly, Fpy is the inertia force along the y direction, which will be acting in this direction. And we have the perpendicular distance will be L sin theta. Therefore, this time will be Fp by L sin theta. Now we have the mass of the pendulum as small letter m. Therefore, Fpx will be m into d square xp by dt square and Fpy will be m into d square yp by dt square. where xp will be equal to x plus L sin theta and yp will be equal to L cos theta. By substituting these terms, we can expand this as in equation number 4. Now by substituting for fpx in the equation 1, we obtain equation 5. Similarly, for substituting for fpx and fpy in equation 2, we can obtain equation number 6. Now in this equation 5, we have this ml theta double dot is there, and here we have expression for ml theta double dot as mg sin theta minus mx double dot cos theta. Now by substituting this in equation number 5, we obtain equation number 7. Then we can take this term to the right hand side, which will give x double dot as in equation number 8. Now in this equation, we have this small letter m is common to all terms, which can be cancelled. And we have x double dot is there, for which we can substitute from equation 8. This will result in equation number 9. And by dividing by L and rearranging terms, we obtain theta double dot as in equation number 10. Now by defining the state variables x1 equal to theta, x2 equal to theta dot, x3 equal to x, x4 equal to x dot, and similarly the input variable u equal to f, and the output variables y1 equal to theta and y2 equal to x, we can obtain the state space model of the inverter pendulum as in equation number 12. So here this is like a fourth order nonlinear system with one input u equal to f, where f is the applied force, and two outputs y1 equal to the angular position of the inverter pendulum and y2 equal to the linear position of the card. In next lecture, we will be discussing the design of model predictive control or MPC schemes for controlling inverter pendulum, in which we will be using the discrete time version of this state space model. These are the references used in this lecture, in which the major reference is this first one. That leads to the end of this lecture. Thanks for listening.